pull some of the heat out of those vapor molecules. They condense. That liquid returns back to the evaporator. There's a certain amount of work that needs to be done in order to physically transport that mass up to the condenser. So if we take a pressure differential, which is slightly higher in the evaporator and slightly lower in the head of the condenser, we end up with a velocity, a certain amount of mass flow through the riser. We start with essentially zero velocity, where the heat is transferred to the alcohol, and the vapors are more or less at 0 meters per second. In the condenser, when they condense, they are at 0 meters per second, but in between, they have to accelerate and then decelerate. And with that acceleration and deceleration, there are incurred losses. So if you have a really small riser, the pressure differential in order to move that mass has to be higher, meaning that the temperature difference between the evaporator and the condenser is higher. So add that to your list of other deficiencies in the performance. I mean, for instance, the temperature difference between the Peltier and the heat transfer paste, the paste to the metal of the evaporator and the metal to, the foil or the screen to the liquid, and then the superheating of the liquid before it actually vaporizes. So then of course the flip side of that in the condenser. So you incur some losses, and the more bends you put in there, if you put any kinks in the tubing, anything like that, it has to increase the pressure differential, which increases the temperature differential. So your delta T between your ultimately your heat source and the environment increases. So you should go for a large pipe for the riser, because you want to keep that velocity down and that pressure drop low. You want to keep that pressure drop very low. So we go for a large pipe. We have as few bends as possible, and what bends there are should be like sweeps. They shouldn't be real hard 90s. So I think this is important to understand for a two-phase thermosiphon. Maybe it's not as important as I think. Maybe it's not that big a deal, and I'm making a big deal out of it. That damn thing went out again. But to continue the idea, the deceleration. Now I have an issue with the deceleration. So you have this increase in velocity in the riser. You have a drop of velocity whenever it exits the riser. So the riser is a tube, 3/8 inch diameter, 1/2 inch diameter, 5/8 diameter, doesn't matter what it is. Whenever it exits that and it goes into the header of this condenser, it's a lot more cross-sectional area. And in doing so, it's going to decelerate. And whenever you have a gas that's going to decelerate, there's going to almost always have to be turbulence. Well, that's kinetic energy. That's kinetic energy lost, and that ends up turning into heat. Now, I don't know if it actually superheats because it's a saturated vapor. That kinetic energy has to go somewhere. But I see it as a potential work lost. And so to try to round this up as much as possible, I felt like there ought to be a way to use the energy source itself to increase the conductivity of the entire device. I have a lot of thoughts about the way exergy works and the way that heat is conducted across any material, whether it's a piece of copper or it's a two-phase thermosiphon or it's a heat pipe. And that if you're really clever about the way that you design the thing, you could actually utilize some of that work instead of wasting it in turbulence and in pressure drops to increase the performance of both your condenser and your evaporator. And my specific interest in the condenser has to do with that liquid being held up, that capillary action that's causing those droplets to just kind of hang out there and plug up some of the microchannels, preventing vapor from being exposed to the cooled surface due to the airflow across the condenser. So I figured if I could increase the pressure differential from the top of the condenser to the bottom, actually make it a little bit higher pressure at the top to essentially force that liquid through, I could utilize more of the condenser. Now, maybe I could do that if I increase the pressure differential between the evaporator and the condenser, such that there's an increase in pressure on the top because the evaporator is running so hot, but that's kind of counterproductive, really. I want to keep that temperature differential small. So I'd almost want to do it locally, just between the top header and the bottom collector on this condenser. And the way that I wanted to try to do that is to utilize that velocity in the riser tube, rather than waste it on turbulence, try to manage it. So if we're going to go from a rather small riser tube, because there's a practical limit to how big I might want the riser tube to be on this thing in a final working device, in practice, if there's going to be an increase in diameter of that between the riser tube and ultimately to the header of the condenser and into the channels, I want to try to manage that, and I could do that with some type of venturi by more slowly decelerating the vapor down into the header. Now, that might be somewhat helpful, but it's probably not going to make a huge difference in the performance of the device, because I don't think I was losing that much in terms of that turbulence. However, I'm still interested in the idea of using some of that velocity in a very simple ejector. So I have other videos on ejectors. If you're interested in ejectors, you could check those out or just do some research on them. But they're interesting little devices, and they're used for all kinds of different applications. But what I wanted to try to do was to utilize a very small discharge. Yeah, I'll go with this one right here. A very small discharge nozzle, primary nozzle. This would be placed within a venturi device, an ejector, really. It's an ejector. You can't see through it there. Anyway, but you can see that it's narrowed there in the middle. And with that rather small mass flow, if properly managed and spat into the ejector throat at the right placement, I could potentially create a little bit of a vacuum on the back side of that ejector. Now, the primary flow, which is the riser, the vapor coming from the evaporator, flows on through the rest of the ejector nozzle into the head of the condenser and is ultimately exposed to the microchannels that are cooled in the condenser, where it condenses out as a liquid. But the back side of the ejector, because I create a slight little vacuum, could be connected to the bottom of the condenser, creating a slight vacuum there. So I'm utilizing some of the velocity, the mass flow velocity of the riser tube to create another loop inside the condenser that essentially pulls the liquid down through the microchannels, or pushes it and keeps it circulating. And the other idea is, utilizing some of that velocity there and conserving that velocity, conserving that work that's done in accelerating the vapor from the evaporator to the condenser in this little loop that's doing something useful, which is removing the liquid so that the liquid is pulled out, pushed out, what have you, separated, falls down the return line, the downcomer, goes back to the evaporator to pick up more heat, while vapor is constantly being circulated. That circulating vapor removes liquid so that, again, the vapor can be exposed to the cooled metal surfaces, but also might increase the heat transfer, just simply because you have moving molecules in there. You're constantly displacing molecules. Might have something to do with the type of flow that exists in there too, disrupting laminar flow, so you have more turbulence in there, so you get more heat transfer. I don't know. I never got to actually really testing the thing to see if I can make it work, because I had too many other issues with contamination, a bad place to work on this thing, and have a full-time job and all this kind of stuff. But I think there's actually something to it. I think it would be kind of neat to be able to fool around with this. And had a lot of other ideas about how to try to do something like this in the evaporator as well, to create this flow in there. And I don't know if I'm ever going to get around to it, but I would like to work with two-phase thermosiphons again someday. Other than that, working with the evaporator, I I think I was getting somewhere with some of the materials that I was using, the construction techniques. I don't think I was getting smooth enough surfaces, good contact there. That would have helped a lot. Better equipment to manage, to monitor this and to test would have been useful. I did have that video last year on the air conditioner, a little incubator thing that I have with the controller, the heater on there to keep the temperature in here at like exactly 22 Celsius whenever I was doing these tests. And it was pretty effective. One last thing I'd like to bring up, if anybody's interested in trying to mess around with this, I don't remember the exact terminology, but there's a electroplating method to increase the surface area on the inside of a copper conductor. If you're trying to, in this case, pass heat from a metal into a refrigerant, there's a pretty nifty technique that was worked out a couple of years ago, and it's been experimented with a little bit by in a university setting. And that was to essentially create these little dendrites of copper on the surface, on the inside surface of the metal. And it was done in a couple of different ways, but one of the ways that I remember, the easiest to describe, involved building an electroplating device, having the surface you want to electroplate, and you want to increase the surface area of facing down in a pool of electrolyte, and then having, what is it? Is this the cathode, the one that actually absorbs the copper? I don't remember, but the other electrode that's being wasted, that's giving up copper ions, is these devices are these electrodes are charged, and those copper ions are deposited on the surface of this plate that we want to increase the surface area of. But in addition to that, tiny little bubbles are introduced of, say, something like argon or nitrogen or something like that, that disrupts the plating process, creates tiny little bubbles and little voids and little pockets. And what it can do is drastically increase the surface area of that metal. But you have to be really careful in the way that you do it. You can easily destroy these little dendrites, and they are, I think most of what I read, once you've done this process and created them, you can do just a normal plating process that deposits another layer of copper on top to kind of make it a little tougher. You have to also keep it really clean because it can, easily harbor all kinds of dirt and minerals and things like that. So there's a couple other methods in which to try to accomplish this, but I think it would be really neat to try to do this, and then even to try to do it on the inside of a pipe, which I think I saw a patent or two on how to go about that. So anyway, if anybody's interested in something like that, to create, really, really super high surface area heat exchangers, hit me up. I might be able to find a couple of the links and shoot them at you. So anyway, that's about it. I'd be surprised if anybody watches this video, but I kind of wanted to just wrap this stuff up and start tearing it down and scrapping it and putting it away, and I would feel remiss if I didn't share it with somebody. So thanks for watching, and if you have any interest... Oh, one last thing. Hold on, I forgot. This is actually in one of the videos. This was one of my later projects right here. This is the downcomer. This is glass. It's a piece of borosilicate tubing. Was designed, obviously so I could see. This is a very low pressure system. This operates in a vacuum, so I was able to do borosilicate and adapt it to copper and build my little trap out of it, but just by heating it up and forming a really, really poor quality bend right there. But I don't think I explained it. I might have explained it in one of the videos here, but essentially all it is, the way I did this, I think this is 6mm glass, so it's right around the same diameter as a 1/4 inch copper tubing there. So what I did was I took a piece of 3/8 tubing, one on either end there. I swaged it open so that I was able to put like 2 or 3 O-rings on the borosilicate tubing after it was bent, and those O-rings are really only to serve the purpose of preventing the epoxy that I poured in around the glass tubing from passing on. Then I did that on both ends. Obviously I did them, in a vertical orientation like that. And then I connected both pieces of tubing just with this flat bar of tubing that I just bent and drilled holes in, and in order to give it some rigidity so that I wasn't putting any pressure on